Building a multi-layer convolutional net. In this section, we will see how to create a multi-layer convolutional network in TensorFlow and watch how a deeper network improves classification accuracy. We will define the layers with TensorFlow layers APIs rather than defining them from scratch. The best practice methods are ingrained in those methods. The import of libraries, datasets, and placeholders can be followed from the previous section. This time, we will use TensorBoard for visualizing the training program. In order to visualize the statistics of the variables, the values of variable statistics have to be added to TF summary. The summaries will be written to a folder that is interpretable to TensorBoard. Let's define a function to write the summaries so that TensorBoard can be used to visualize them. Function to write the summaries so that TensorBoard The variable summary function writes the summaries of a variable. There are 5 statistics added to the summaries: mean, standard deviation, maximum, minimum, and histogram. Summaries can be either a scalar or a histogram. We will see how these values can be visualized in TensorBoard when logged for several variables. Unlike the previous model, we will resize the MNIST data into a square and use it like a two-dimensional image. The following is a command to reshape the image into 28 image pixels by 28 image pixels. The dimension -1 denotes that the batch size can be any number. Note that there is an argument called name that will be reflected in the TensorBoard graph for ease of understanding. We will define a 2D convolution layer where the input, filters, kernels, and activations are defined. This method can be called anywhere for further examples and is useful when the activation function has to have rectified linear unit ReLU activation. The convolution function layer is defined as follows. There are default parameters for kernel _size and activation. The summaries are added to the layer within the function and the layer is returned. Whenever the function is called, input _layer has to be passed as a parameter. This definition will make our other code simple and small. In a very similar way, we will define a function for the pooling _layer as follows. This layer has default parameters for pool _size and strides to be 2, 2, and 2 respectively. These parameters generally work well but can be changed when necessary. The summaries are added for this layer too. We will next define a dense layer as The dense layer defined has default parameters for activation and variable summaries are added as well. The pooling underscore layer takes the feature map from the convolution layer and reduces it to half its size by skipping, using the pool size and strides. All these layers are connected as a graph and are just defined. None of the values is initialized. Another convolution layer will be added to transform the sampled features from the first convolution layer to better features. After pooling, we may reshape the activations to a linear fashion in order to be fed through dense layers. The only difference between the convolution layers is it's important that the dimensions change appropriately from layer to layer. Choosing the parameters for kernel and stride are arbitrary and these numbers are chosen by experience. Two convolution layers are defined, and this can be followed by a fully connected layer. A dense layer API can take any vector of a single dimension and map it to any number of hidden units, as in this case is 1024. The hidden layer is followed by ReLU activation to make this a nonlinear computation. Variable summaries are added for this layer as well. This is followed by a dropout layer with the rate of dropping out. Keeping this high will stop the network. The training mode can be set to true and false based on when we use this. We will set this as true, default is false, for the training. We will have to change this while the accuracy is calculated. Hence, a bool is kept for this, that will be fed during training. The dropout layer is fed again to a dense layer, which is called logits. Logits is the final layer with activations leading to the number of classes. The activations will be spiked for a particular class which is the target class and can be obtained for a maximum of those 10 activations. The logits output is very similar to the model created in the previous section. Now the logits can be passed through the softmax layer followed by the cross-entropy calculation as before. Here, we have added a scope name to get a better visualization in tensor board as follows. This loss function can be optimized with TF train APAS methods. Here, we will use the adder. The learning rate need not be defined and works well for most cases. The accuracy is calculated as before, but name scopes are added for correct predictions and accuracy calculation. A scalar summary for accuracy is also added. The next step is to start the session and initialize the variables as in the previous section. The lines are not repeated here. The summaries have to be merged, and the files for writing the training and testing summaries have to be defined. Note that the graph is written once with the summary_writer. The training is very similar to before except that the accuracy calculations while training and the values are added to the summaries. Next, the data can be loaded in batches and training can be started. Summaries are returned in every iteration for training data and are added to the writer. For every 10th iteration, the test summaries are added. Note that the dropout is enabled only during training and not during testing. We have completed the definition and summaries of the network and this can be run. To see the training process, we can go to TensorBoard.